All right, so we're going to look at the types of questions that might be involved in nuclear chemistry mastery. So for this mastery, we want to be able to identify types of nuclear reactions used for dating and balanced nuclear reactions, and explain how radiometric dating works and why different elements are used for dating different objects, including the percent of an isotope measured in an object to estimate its age. And here are the equations right at the top that we're going to be using in this mastery. All right, so let's start by looking at some balancing nuclear equations. So this first one, we see that neptunium is turning into a helium nucleus and some element. We want to figure out what that is. So first of all, looking at this, we see that helium is one of the things that's given off. So we know that this is a type of alpha decay. And when we're balancing nuclear reactions, we want to make sure that the mass number, the total mass number on both sides of the equation is the same, and the total atomic number on both sides is the same. So if this side is 237, then the other side needs to be 237 as well. So 237 is equal to 4 plus some number, and we know that that must be 233. So we know that this mystery element has a mass number of 233. And similarly, if we look at the bottom, we know that 93 has to be equal to 2 plus some number. And we can see that that number is 91. So we then would look at the periodic table. And if we look at the periodic table, we see that neptunium is element 93. And element 91 is protactinium, and its symbol is Pa. That might look like Pennsylvania, but it's not. All right, let's look at this next one. This is the other type of decay we've looked at. We see that what is being spit out is an electron, and we know that this is beta decay. And the same rules apply. We know that our mass number has to be the same on both sides, and we know that our atomic number needs to be the same on both sides. So if this side is 13, and on the other side we have a 0, well then this mass number must stay 13. 13 equals 0 plus 13. And then we're going to look at our atomic number, which is 7. And we know that 7 is equal to -1 plus whatever number that is. And so that must be 8. And if we look at the periodic table, we see that the element with an atomic number of 8 is oxygen. All right, so now we're going to look at the half-life of a uranium decay reaction. So let's first think about what half-life really means. So let's assume that we started with 100 grams of a radioactive element. And we know that the half-life is equal to 4 years. Well, if that's the case, at time 0, so when we're starting out, we would have 100 grams. After one half-life, which is 4 years, we would use up half of that 100 grams and we would have 50 grams left. After 2 half-lives, so now we have, it's 8 years have passed, another half of this is gone and we're left with only 25 grams. After 3 half-lives, so now we're at 12 years. Half of this again is gone, and we're down to 12.5 grams. And so we could continue going like that. However, it's not always so convenient that we're moving in exact half-lives. So we want to be able to know, how much time has passed, how much we have left, no matter the amount of time that's passed. So to do that, we're going to have to look at what the rate constant is, and then we're going to have to use our integrated rate laws to be able to find that amount. So let's go ahead and look at question 3. And it tells us if the half-life of a uranium decay is 120 seconds, the first thing we need to do is find the rate constant. So let's go up and look at our equations at the top. And right here, there is our equation to be able to find the rate constant. So we know that K is equal to the natural log of 2 at T over divided by T 1/2. And remember, when we say T 1/2, that 1/2 is a label. It's telling us what time 1/2. It's not a numerical value there. It is a label of what time we're referring to. All right, so let's go ahead and put in our values for this. We know from the question that it tells us that T 1/2, the half-life, is equal to 120 seconds. So let's go ahead and put that value into our equations. We have the natural log of 2 divided by 120 seconds. And that's going to give us 0.00578 per second. And there is our rate constant. So it tells us that we started with 15 grams of uranium, and we want to know how much time must pass before we have 0.1 grams left. So let's go ahead and look at our equations, and we can see that this equation is the one we want to use. This equation and this equation are the same thing. They're just represented differently, but they mean the exact same thing. So we're going to go ahead and use this version. It's a little bit easier when we're trying to find time. This one is a little bit easier when we're trying to find how much we have left. All right, so the natural log of the amount left after a certain amount of time is equal to the negative rate constant times the amount of time that passed plus the natural log of however much we started with. All right, so let's go ahead and see which variables we know. We know that we started with 15 grams of uranium. So N naught, or N initial, is equal to 15 grams. We know that after a certain amount of time passes, that we are left with 0.01 or 0.10 grams. And we just found in part A that our rate constant is equal to 0.00578 per second. So those are the variables we know. So what we want to go ahead and do is isolate the variable that we don't know yet, and that variable is our time. So I'm going to go ahead and subtract the natural log of N naught from both sides. And then that'll cancel. So I have the natural log of the amount after some time minus the natural log of how much I started with is equal to negative KT. I'm now going to divide both sides by negative K. And those cancel. And we get the natural log at the amount at some time minus the natural log of how much I started with divided by negative K is equal to T. All right, so now I'm going to go ahead and plug in my values. So this will be 0.010 minus the natural log of 15 divided by negative 0.00578 per second will be equal to time. And if I go ahead and do that calculate, I'm going to get that my time is 1,270 seconds. Now, if you could do this on your calculator, you might get 1,265 or 1,267. Those are just rounding differences. If we go to 3 significant figures, we're looking at 1,270 seconds. And that's going to be how much time has to pass until we're left with 0.10 grams. All right, so back up at the question at the top, it said I can explain how radiometric dating works. So let's think about this with regards to radiometric dating. Something with a half-life of 120 seconds would be, well, pretty useless for this. But if you can imagine something that had a half-life of 8,000 years, and it was something that was in a biological system, we would know how much something that was alive should have. And we can look and see how much is remaining. So we would know how much we should have started with. We would know what percentage is in an object that's normally left. We would know how much we ended with. We would be able to measure that. And for a given isotope, we know the rate constant, which means that we could solve for T. And we could figure out how old that object is by using radiometric dating. And that can be really useful when looking at archaeological dig sites about pottery or bone, or looking at preserved mammoths that they find in the permafrost. All sorts of cool stuff. All right. So if you have any questions, please do email me, and I'm happy to help. Thanks.